So in this video, we're going to look at the 3 laws of thermodynamics and connect those to spontaneity for a chemical reaction. So we're going to talk about these 3 laws, look at some applications, specifically one of them, how it correlates maybe to Gibbs free energy and how that connects back to the spontaneity of a reaction, and then being able to predict from the thermodynamics of a reaction the spontaneity of that reaction, and specifically looking at our entropy change and our enthalpy change. Now, as we're doing this, we want to see, well, let's start with some data that we have about enthalpy and entropy, and maybe make some observations about what is favorable for something to be spontaneous. And again, reminding us, if something is spontaneous, that is a process or a reaction that occurs without any continuous added resources or energy. And so if we're looking at this reaction here, we want to think, will this just happen if these 2 reactants or 3 reactants get together? Will that happen without anything else, any added energy per se, to let continue to happen? So here we have some data, and this data tells us that this reaction here is spontaneous at all temperatures. And what we observe here is a negative delta H and a positive delta S. So our entropy is increasing and we are releasing heat. Then we have our second one here is N2 liquid to gas. So we're basically undergoing vaporization. So we're undergoing this phase change. And this is only spontaneous above a certain temperature. So it's not going to happen at any temperature. It only happens at above negative 196 degrees Celsius. Well, then we notice here we have a positive delta H and a positive delta S. And so we see, well, maybe because we've shifted the sign of what our delta H is, now we're absorbing energy in the form of heat. That's going to be affecting the way that that reaction is spontaneous or not at different temperatures. Then our third one here, we have N2 and O2 going to 2NO. And that is non-spontaneous at all temperatures, that specific reaction. And again, we notice here that we have a positive delta H, and a negative delta S. So now we see here, and we look at an observation, this is always non-spontaneous. And then the last one, we have HI going to H2 and I2, and this is only spontaneous below a certain temperature. And here we notice we have a negative delta H and a negative delta S. So maybe some observations that we can see when we're dealing with maybe something being non-spontaneous or spontaneous at certain temperatures is that things that are possibly favorable that we may consider would be looking at something where we have a delta H that is negative, right? We're releasing heat. We notice that that is something that's favorable here. Or a delta S that is positive. We're increasing in entropy. And so now as we have this reaction occurring, we have the ability to identify the relationship there. And if we have conflicting, like favorable results for our delta H or delta S. So for example, we have a positive delta H and a positive delta S. Well, that positive delta H is not favorable for spontaneity. But we do have a positive delta S, which is favorable for spontaneity. And so we notice there is some temperature dependence. And so if we look at this here, when our delta H and our delta S are the same sign, so either both increasing or both decreasing, we notice that there is some temperature dependence of our spontaneity for this reaction. Now, as we're looking at this, hopefully we have the ability to identify some information on why there's this relationship between the spontaneity of the reaction and our delta H and delta S values. But we do notice that there is some important contributions of our delta S and our delta H to our reaction. Now, these different variables are included in some of our 3 laws of thermodynamics. So let's look at these 3 laws and see what kind of applications that we can make about these 3 scientific laws. And remember, a scientific law, if we're thinking about this, is a broad generalization of observations or data. So we've made lots of observations or collected a lot of data, and these are the observations we can make. These are the broad trends that we observe. The first one is the first law of thermodynamics, which we've used a lot when we've looked at heat transfer, is that energy cannot be created nor destroyed. So one of the observations that we can make is that something like the Q of a reaction is equal and opposite to the Q of the surroundings. So heat lost by a reaction or gained by a reaction, that's going to be transferred to the surroundings or taken from the surroundings. And so heat is transferred between those things. It's saying basically the change in energy of our reaction is going to be equal and opposite to the change in energy of our surroundings. We're looking at these energy changes. We can't create energy and we can't destroy energy. It's going to be converted between possibly different forms. Maybe we're going to convert between thinking about heat transfer and thinking about maybe bonds being formed or broken as we're looking at reactions. So again, we're looking specifically at reactions here and the possibility of kinetic energy and potential energy interchanging between each other. Now the next two of those laws deal with entropy. Well, notice entropy is very important when we're thinking about reactions. And again, we've done a video already talking about an introduction to entropy. So we have this broad idea that entropy is how energy is distributed in a system or surroundings. And what we'll notice here is that for any spontaneous process, we just talked about spontaneous processes, the total entropy of the universe increases. So the delta S of the universe increases. And I think when we see this idea of the universe, that's like a big idea in thinking, well, how do I narrow this down to what I'm actually dealing with a reaction? So what we want to do is we kind of want to break it into two parts that we think of for entropy change. So the entropy change of the universe is equal to the entropy change of the system plus the entropy change of the surroundings. And a lot of times we're treating our system, we can think about that as the delta S of the reaction. So let's connect this back to what we've already talked about with regards to entropy. Again, we've said entropy is basically a measure of energy distribution within a system or in the surroundings as we're looking at it. So if we increase the amount of energy distribution, we've increased our entropy and vice versa. So we have the ability to look at the delta S of a reaction, maybe looking at how our physical states change, number of particles, etc., that we looked at in a previous video. But now we don't have any per se information that deals with the change in entropy of our surroundings. Well, what we do know is that the change in entropy of the surroundings is equal to the Q of the surroundings divided by the temperature that surroundings is at. Now we look at the Q of the surroundings. Again, we're not looking at it through one lens of just the system or just the surroundings. We're still now thinking about the delta S of the surroundings and the delta S of the system. So our reaction and our surroundings. But what we can see here is we think, well, what if we look at this idea that we just addressed right here? If we bring that and connect it back here, we could say the delta S of the surroundings is equal to the opposite of the Q of the reaction at a specific temperature. So now we have some information that tells us something about just the reaction. We have it through one lens. Now if we clean this up a little bit and clarify this as we're looking at a specific reaction, we can say the delta S of the universe is equal to, again, the delta S of our system, which is our reaction, minus Q of the reaction divided by temperature, right? And that's what we have here when we're looking at it. Well, again, we're looking at heat. Maybe we want to connect it back to, we were originally talking about enthalpy. And one important thing that we can look at is that if we're looking at a reaction at constant pressure, we know that the Q of the reaction is equal to the enthalpy change for the reaction, how much heat is released or absorbed when that reaction occurs at constant pressure. So if we go ahead and put that in here, we see that the change in entropy of our reaction plus, let's leave it as our minus, the change in enthalpy for the reaction at a specific temperature. So now we know that that is the entropy change for the the universe and how it corresponds to the spontaneity of a reaction. Now what we know is that that has to be greater than 0. The sum of those two components has to be greater than 0. Well, if we think we want this to be positive, effectively, the favorable, or importantly, like the thermodynamic values of delta S and delta H that contribute to it being positive would be a positive delta S, so increasing the amount of entropy for the reaction, and a negative delta H, right? Because if we subtract a negative, it makes it positive. And we just made that observation earlier in saying, well, a positive delta S and a negative delta H, those are favorable for the spontaneity of a reaction. So if both of those are true, if we have a positive delta S and we have a positive or a negative delta H, that means that we can only have, no matter what temperature we're sitting at here, we can only have a positive delta S of the universe. So we'll always be spontaneous no matter this temperature dependence. But we do notice that there is this temperature dependence if our signs of our delta H and delta S are not this favorable contribution of both one positive, one negative, or one negative and the other positive. So now we have this observation that this leads us to a positive delta S and a negative delta H for our reaction is favorable for spontaneity. Now, again, we can think about the delta S of the universe, and that being positive, again, is a really big idea. So what we want to do is we want to connect it to another thermodynamic value that connects our delta H and our delta S. And that would be Gibbs free energy. So Gibbs free energy is the free energy change for a reaction. And what we'll notice when we're looking at the Gibbs free energy, it includes information about our delta H and our delta S for the reaction. Now, if we look at this, we see, well, then something that might be helpful is to know that a specific sign of delta G is going to give us a spontaneous process. And this is like the idea that the delta S of the universe is greater than 0. We can connect these two is that when the delta S of the universe is greater than 0, the delta G of the reaction will also be less than 0 or negative when we're looking at this, right? We're looking at a positive delta S or a negative delta G is going to give us a spontaneous reaction. And so now we have another way that we can look at spontaneity is that if our delta G is negative, that would be a spontaneous reaction. If our delta G is positive, that would be a non-spontaneous reaction. Now, why is this the case? If we were to kind of go through a little bit of a derivation here, and if we wanted to, we could clean it up a little bit, but that would lead us to a relationship similar to delta H minus T delta S. We effectively would just kind of multiply this T across and give us that T multiplied by the delta S instead of divided by the delta H. And that leads us to the observation that a negative delta G is a spontaneous reaction and a positive delta G is a non-spontaneous reaction. And why does that relate to this idea of free energy when we're looking at a reaction? Now, the reason why we can think of it as corresponding to the free energy is that our Gibbs free energy, this is the energy available to the surroundings or free energy released for this reaction. So if we have a decrease in Gibbs free energy for the reaction, that means, what that tells us is that there is now free energy available to the surroundings to do work. So that's what our Gibbs free energy is. It tells us something about this idea of energy available to the surroundings to do some amount of work, to do something with it, right? And then what that work could be, that's something like power our cell phone. It could be something along the lines of running, powering a fuel cell. There's all these different things. Or looking at energy in our biological systems, thinking about maybe ATP, ADP reactions. Those are all free energy. Energy available to do something, move an ion through an ion pump within a cell, right? So there's this free energy of reactions that are available to do something with it, right? And that's what work we would classify as work. And we see that this is an application of the second law because the sign of delta S for the universe tells us about what sign we would get for our delta G to make it spontaneous. And we're going to look at an application of this a little bit later in this video. Now let's look at our third law of thermodynamics. This is saying at absolute zero, the entropy of a perfectly ordered crystalline substance is zero. So at basically our lowest possible temperature we can get to, 0 Kelvin, the entropy is zero. Now what does this mean for us in a kind of an application here and why this is important? Well, what this means is that at any temperature greater than temperature equals 0 Kelvin, all compounds or substances will have some inherent positive entropy value. So this is, we basically now have what we would classify as our sea level. Unlike enthalpy, enthalpy is not necessarily zero at 0 Kelvin. Gibbs free energy is not necessarily zero at 0 Kelvin. But the entropy, right, the ways that we can distribute energy, there's basically only one way to distribute that energy because they're not moving around, right? We know that our temperature Kelvin is directly proportional to our average kinetic energy. So if our temperature is 0 Kelvin, that must mean our average kinetic energy is 0 as well. So we basically have no moving particles in this perfectly ordered crystalline substance, and so therefore the entropy would be 0. So one of the main consequences here that we can observe is that we have the ability to look at the change in entropy for a reaction is equal to the sum of all of the standard entropies. So these would be tabulated known inherent entropies. And again, this is at 25 degrees Celsius. That's why we have that standard value there. For our products, minus the sum, again, this sigma is representing the sum of, and N is the number of moles of each reactant or product, times the standard entropy of our reactants. And again, we can think of this as being basically the final entropy minus the initial entropy of our system. So we're looking at the ability to quantify our entropy change by looking at the entropy that we end up with minus the entropy we started with. And we're going to go ahead and look at an application of this one and the second law of thermodynamics together. Well, now that we have these ideas of these three laws of thermodynamics, let's see how we can maybe apply them. So first thing we're going to do is we're going to answer some questions based upon this reaction. So we have 2 moles of hydrogen iodide gas producing 1 mole of hydrogen gas and 1 mole of iodide solid. Qualitatively, we have the ability to predict delta S should be negative. We're basically going from 2 moles of gas particles to 1 mole of gas and 1 mole of solid. So we have the same number of particles, but we now have gone from a gaseous to a solid physical state, and we know that the solid physical state has a lower entropy than a gas. So we know that once we calculate the delta S, we should see a negative value for that delta S. We're going to go ahead and do that from standard entropies. And again, these are all in a table that we have the ability to look up and find their standard entropies. So I'm going to go ahead and rewrite our reaction here and show the entropies that we would see for each of these. So again, we have our hydrogen iodide gas producing H2 and I2 solid. I'm going to go ahead and delineate between our products and our reactants. So if we go to a table, we find that for HI, we're going to have a value of 206.6 joules per mole Kelvin. So for every 1 mole of HI, we're going to see that we're going to have 206.6 joules per mole Kelvin of that. And then we notice that we have, importantly here, 2 moles of our hydrogen iodide. So effectively, the entropy that we start with our 2 moles of HI, would be 413.2 joules per Kelvin. And we can think of this as being the initial amount. We can think of this as being for all of our reactants. So now that's how much we start with. And let's figure out now how much we end up with our products. So our H2, we go to a table and we find it's 130.7 joules per mole Kelvin. And we notice that we have 1 mole of H2. And we also have 1 mole of I2. And we go to a table and we find that 1 mole of I2 as a solid is 116.14 joules per mole Kelvin. And so we add those together and we find that we have 246.84 joules per Kelvin. And again, we think, well, what is that? That would be for what we end up at the end or for our products. So what we want to do is we want to say, well, if I want to calculate the delta S, it should be the sum of the standard entropies of our products minus the sum of our standard entropies of our reactants, or what we finally ended up with minus what we started with. And so this is going to be our 246.84 joules per Kelvin minus 413.2 joules per Kelvin. And so we would find that our change in entropy here would be negative 166.36 joules per Kelvin. So we see here that our change in entropy was negative as we predicted, but we had the ability to quantify it by looking at the sum of all of our reactant entropies, the sum of all our product entropies, and we took what we ended with, so our products, and we subtracted from what we started with, and that tells us our change. So now that we have this information, we're going to be able to use it in some way to look at the entropy change of the reaction and how it corresponds to the overall spontaneity of our reaction. Now our second question is looking at the entropy of the surroundings. Will it increase, decrease, or remain constant when this reaction is completed at 25 degrees Celsius? Now one important thing to note here is that entropy, again, is not energy. Entropy is the measure of basically energy distribution, or how it's been distributed across a system. So what we cannot say is we cannot say the entropy, the change in entropy of the system is equal and opposite to the change in entropy of the surroundings. Okay, the reason why we can't say that is because we're not looking at one thing losing entropy causing something else to gain entropy, right? We can have the entropy of the system and the surroundings increase. We can have them both decrease. It has everything to do with the transfer of the energy from the system to the surroundings and how possibly that leads to an increase in distribution of energy or a decrease in distribution of energy. And we already had mentioned that the change in entropy of the surroundings is equal to the heat that's gained by the surroundings at a specific temperature. Well, we also said, because we already talked about this, that is actually also equal to the change in enthalpy of our reaction at a specific temperature. Well, we know that our enthalpy change here is negative. So if we wanted to, we could go ahead and calculate this, or we can just qualitatively say negative 53.2 kilojoules per mole and divided by 280 Kelvin. So this is our temperature in Kelvin. So we could say that it increased by 0.1785 kilojoules per mole Kelvin, right? So it's a positive value. Or what we would notice is that every exothermic reaction is going to release heat to the surroundings, and that's going to cause an increase in the surroundings entropy. We've given it more total energy to distribute, right? We think, why is this the case? Why is it causing the surroundings entropy to increase? We have more energy in the surroundings that is going to be able to distribute, and that's going to lead to an increase in entropy of our surroundings. And we see we have the ability to do that based upon whether heat is given to the surroundings or heat is taken from the surroundings when this reaction is occurring. So when we're looking at the spontaneity of a reaction, whether a reaction is spontaneous or not, there's two ways for us to be able to look at this. We can look at the entropy change of the universe, or we can look at the Gibbs free energy, right? And the Gibbs free energy has to be less than 0, and the entropy of our universe has to be greater than 0 when we're looking at this. So the entropy of the universe has to be positive, or the Gibbs free energy has to be negative. What we'll notice is that a lot of times it's really helpful just to focus on the Gibbs free energy, because it tells us a little bit more information also about energy available to do work for the surroundings. And so now let's go ahead and let's calculate that based upon what we know for our reaction. So let's figure out, is the Gibbs free energy positive or is the Gibbs free energy negative? So the Gibbs free energy change is equal to the enthalpy change minus the temperature that we're at in Kelvin times the change in entropy. So let's plug in the information that we have. Negative 53.2 kilojoules per mole minus our temperature 298 Kelvin times our entropy change. Now we calculated our entropy change to be negative 166.36 joules per mole Kelvin for this reaction. Now one important thing to pay attention here, that's units of joules, that's units of kilojoules. And so we either need to convert our kilojoules to joules or our joules to kilojoules to make sure we're adding the same energy units together. Well, let's go ahead and just convert this to kilojoules. So we divide by 1,000, negative 0.16636 kilojoules per mole Kelvin. So we go ahead and plug that in here, negative 0.16636 kilojoules per mole Kelvin. And so now when we multiply these together and then add them, we will get kilojoules per mole for each of these. And so we would get a Gibbs free energy change of negative 3.6 kilojoules per mole. Well, since we know that our Gibbs free energy change is now negative, that lets us know, yes, this reaction is spontaneous at 298 Kelvin. Now we want to also answer the question, now that we've identified that it's spontaneous at that temperature, will it always be spontaneous? Is there a temperature where the spontaneity maybe changes? Will it be non-spontaneous at one point and then spontaneous at another point? And so now when we're doing this, let's identify that and see if it is temperature dependent, what temperature will the spontaneity change? So again, our Gibbs free energy change here is our delta H minus T delta S. Let's just do a little bit of qualitative analysis here and looking at the numbers that we have. So we have a negative delta H, we have a negative delta S, and our temperature is always positive because it's a Kelvin temperature. We cannot have a negative Kelvin temperature. And so what we notice is that if we look at this reaction here and the thermodynamics that we have, our delta G could be positive or negative, and that depends on the relative magnitudes of our delta H versus our T delta S. And we notice that that is going to be the same at all temperatures for the most part. It's not really going to fluctuate that much, but we notice here that this is where our temperature dependence comes in. So we notice that there's this temperature component here. And we see here there's a possibility for our delta G to be negative or our delta G to be positive. So because there is a possibility for it to be negative or positive, depending on the relative magnitudes, that would let us know that this reaction is temperature dependent. At some temperature it could be a negative delta G. At some temperature it could be a positive delta G. Now what temperature does that occur at? If we think about, if we're calculating the temperature that it possibly happens at, if we go from positive to negative or negative to positive, we have to go through delta G equals 0. So if we go from negative 0.001 to positive 0.001, we're going to go through a delta G value of equal to 0. So when our delta G is 0, that tells us that would be the temperature where our spontaneity for the reaction changes. So maybe below a certain temperature is spontaneous, or above a certain temperature is spontaneous. Depends on the signs of our delta H and delta S. So let's identify what temperature this spontaneity changes. So we know our delta G is 0. We need to figure out the temperature where the spontaneity changes. So let's go ahead and calculate that based upon the information that we have. So again, we have our delta S and delta H. So I'm going to do the opposite, and this time I'm going to convert my delta H to joules. So I'm going to have negative 53,200 joules minus the temperature in Kelvin times our delta S. So again, 166.36 joules per mole Kelvin. And so now we're going to go ahead and we solve for our temperature, and we get a temperature of 319.8 Kelvin, but we were asked maybe to identify this in degrees Celsius because it's a temperature scale that we're more familiar with. And so we can find our temperature in degrees Celsius is going to be this 319.8 Kelvin minus 273.15. That helps convert between our degrees Celsius and Kelvin, or vice versa, and we would get 46.6 degrees Celsius. So that's the temperature where our spontaneity changes. And we'll notice negative delta H, that's going to tell us if this is smaller here, this T delta S, if that is smaller, that would mean that we're going to overall end up with a negative value, and it's going to be a reaction that is spontaneous at that lower temperature. So we'll see here, because our delta H is negative and our delta S is negative, that means below 46.6 degrees Celsius, our reaction is spontaneous. And above that temperature, it would be non-spontaneous. That's the temperature where we flip between spontaneity of this reaction. So I hope this video gives us an introduction to these three laws of thermodynamics, and will hopefully give us the ability to apply them with Gibbs free energy, as well as looking at the standard entropies of our reactants and products.